Hello monkeys, how y'all doing? So today we are gonna be doing some batteries and capacitors. So the first thing I'm gonna start with is conductors. You know what? Let me make this a little bit bigger. Right, that's the first thing I'm gonna start with. And so the conductor is something that's like, let's say, metal. I'm gonna give it a weird looking shape like this. And on the when it's neutral, it just looks like this, just neutral. But when it's negative, obviously the negatives will go on the outskirts, or when it's overly positive, these will go all the way outside here. Right? And we spoke about this from Coulomb's law in the very first few units. Alright? So now, as you can see, this is distributed almost evenly, except in corners, it's not. So what is the electric field that this object creates? Well, you see when I used to have an electron, we said it goes like this, right? So if I had a bunch of them, then it's the same thing, just off the surface of this object. However, out of these sharp corners, you have a bigger, well, there's more of them, so you have a bigger electric field out of sharp corners. Okay, just because there's more of them. Right? Now, what is the electric field inside? So inside, what I mean is, ignoring this, the zeros are the outside. Inside here, what is the electric field? Well, that's just E equals 0. Now, why is because remember how in Unit 1, and if you're not familiar with this, go watch Unit 1, and we said the electric field inside stabilizes. There's pluses and minuses, pluses and minuses, pluses and minuses. They stabilize, cancel out each other's electric field, making it 0. But obviously all the excess ones stay on the outskirts. So on the outskirts there is some E coming out, therefore that's why there's an E. But in the inside it's all balanced out. So inside the conductor it's 0. Alright. Now the question is, well, if that's 0, what is my potential difference? So let's say I have a point here, V1, and a point here, V2. Well, what is the voltage, the volts, or the potential, electric potential at this certain point? Well, it's probably going to be something, right? There is going to be some electric potential. Don't think there's none just because the electric field is 0. It has nothing to do with it. Remember, our volt is K, Q over R. And so, if there was a charge here, well, there's a bunch of charges. So I'll have to add all the charges at this particular point, some distance R away, and that would be my V1. But if I chose this point and this point, what is the change? And remember how I said there's a bunch of pluses and minuses all the way around that stabilize each other? So since they stabilize each other, that means the potential, the electrical potential is the same everywhere. So this is V3 is the same as V1. The density plus minus is the same everywhere. And so then the voltage, the electrical potential is the same everywhere. That means the difference between 2 points, well, if this was, let's say, 100, and this was 100, then the difference between the two is 0. And so that is true. So a couple things. Inside, conductor, our voltage is constant everywhere. Our potential difference is 0. And our electric field is 0. Right? So now that we're done with conductors, we're going to move into either capacitors or battery. I haven't made up my mind yet. Okay, so the first thing I'm going to go through is batteries, actually. And so let's draw a quick typical battery and explain how does a battery works. And it's actually much simpler than you might think. Let's get that going straight down here, across, and all the way up. So the battery is usually split into 3 parts. That's the first part, and that's the second part. Now one side is negative, as we know. The other side is positive. Now what's in the middle here is some chemicals. Okay? Now the way this works is these chemicals will create a lot of electrons and I'll put them here. All right? Now, as we know, well, usually in physics, they'll teach you that electrons actually will move from here to that side, but that's actually a wrong misconception that we've been using because the guy who started it did it this way, and now we've been following it. But realistically, this is how it works. So these negatives all the way, they all add up here, and they obviously want to move and go to the positive here, but they can't because this chemical is in the middle. So they're just stuck there, and there's a lot of force. There's a lot of potential, electrical potential. Remember how I said when I give you a positive, and I give you a, let's use this one, and I give you a negative, well, a positive, well, negative and positive. And if I take this and I take it closer, the potential decreases. But if I take it further, you see, if I take it further here and I leave it, I'll snap back. If I drag it here and I leave it, I'll snap back. And so that's what they did. Using these chemicals, they grabbed a bunch of these and they shoved them in here. And as soon as they release them, they want to go to the positive, but like there's a chemical in the middle, so they can't. So what we're going to say is, well, then as soon as I connect these with a wire, now they have a path to flow and go to the positive and, you know, match with their opposites attract. And the reason this happens is because of the potential difference. I use a lot of energy to shove those in there and force them in here. So you see, if I have another positive here, I'm going to use a lot of force to put it here. And then what I'm going to do, I'm going to grab another one and then put it in there. And then grab another one and then put it in there. And then so on. And obviously I use a lot of force to put them in there. And so this force adds up and it gets stored. As soon as I connect it, this force starts moving. And that force is my volts. That is my potential difference. And that's why they usually tell you, like, some batteries 10 volts. That means there is that much potential energy in there. So that when you connect it, these 10 volts will start moving. And that's how many joules per coulomb you'll get. And how many coulombs are there? You know, there's millions, if not billions. And the movement of these electrons moving along the wire is what actually generates electricity. It's not the electrons themselves. It's the movement of these little electrons. All right. And so they'll move and they'll go up here. And so I'll have some potential difference of 10. Well, here, before I turn it on, so you see right here, at the tip, so if I remove everything, at the tip, I know I shoved here. Remember when I told you there's a conductor, and inside the conductor there's some volt? Now the E is 0. The E in here is 0, like we said earlier, but the volt you can have, right? That's what we said. We said we have volt. The potential difference inside is 0, but there is some voltage. And so here, inside this section, we have some voltage. Let's say it's 10 voltage, right? So that's how much we have here. Here, well, there's no force. We don't have anything. We just have one positive, let's say. We'll remove the negatives. And so I have 0 volts here. And so remember how we said electrons or protons flow from high potential to low potential. It's the same thing as gravity, where if I put a ball here, it'll roll down because there's, well, your equation is mgh, and because of the height, now I have some gravitational potential. When I let go of it, it'll roll down where the potential is 0. And so that works, and so that works the same with a battery, where when I unlock this and I let them flow, then they'll start flowing. And so what is my potential difference? Well, it's the final minus the initial. And so 10 minus 0 is just, I have 10 volts. And that is my potential difference. But over time, when these keep moving, and they balance out, where I'll have just enough electrons here, I have just enough protons there, just so that it's all neutral. Now, well, if this, now I have a potential difference of 0, because if I remove all this, after it all evens out, then I won't have any more electrons here because they all went to the positive and they mashed up. And so, well, how many do I have here? I have 0 volts. And here, well, they're not really struggling for positives. Each negative got its own positive. So, well, here is also 0 volts. And so the potential difference becomes 0. And that's when you don't get any energy. And that's how the, that's how a battery works. And he also mentioned a quick little side note, What is happening here when I'm separating them, well, when I have the positive end there, and here what I'll have is negative. And by the way, inside your battery, usually what you'll have is this little pole goes all the way down, like this, and half of it is positive. It's like, it's a cathode, I believe, and the other half is negative. It's an anode, and I believe it's like permanent. So this is what pushes these out, and the chemicals. But anyways, that's beside the point. Actually, let me take it out of the way so you guys don't get confused. So what the battery is doing is charge separation. Well, there's a bunch of positives here as well, right? This is charge separation, and really all there is for charge separation is this. And obviously they create an electric field that goes from the positive to the negative. Just typical charge separation, to be honest. Just like when we were talking about capacitors, one was positive, one was negative. They separate positive and negative. Now you might ask yourself, well, how does this happen? You know, in a battery, we're doing it chemically. There are probably other advanced methods that they use nowadays to separate them. But, I mean, we're not really studying that. We're studying the physics of it, which is how the voltages move and the electrons move and all that. But just so you know in mind, charge separation is just when you separate the charges so that the one side is negative and one side is positive. All right, so now moving on to capacitors. What is capacitors? We've been working on them recently, actually a lot. And let's draw our capacitor. It's two parallel plates. Nothing too complicated. This is actually a pretty easy unit. If you want to get your marks, this is the unit you'll get your marks from. If he includes it, of course. All right, and so this is usually what this is negative. This is usually what a capacitor looks like. This is all throughout, by the way, for both sides, okay? And so when I connect these together, what I get is a, well, potential difference. Of course, I'll actually put that in green. So what I'll get is a potential difference. Remember how we said this is 0V, and this will have like 100V, and so I'll have a potential difference of 100 volts, right? Now, what is the electric field inside here? Well, it goes from positive to negative, right? And you see, between these two plates, if I drop an electron here, then this electron will stay there. But if I drop the electron here, it will bounce there. And if I do the same thing with my, what do you call it? With my proton, which is actually what they usually take to use as reference. If I drop it here, then I'll go to a place of lower potential, which is here, right? And so that's usually how it works, and that's really capacitors. Now, capacitors, when they make them actually, right in the middle, they put an insulating material, so electrons will never go across. They'll just kind of hang on this plate, and then what they'll do is they'll take this plate. Oh, nice, we have a battery up here. They'll take this plate and they'll actually connect it to this battery. Actually, let me bring this beautiful art up there. And you see what they'll do is, well, actually, now I'm going to take the whole art and bring it down a little bit. Whoop. Okay, so now what they're going to do is they're going to take this and plug it in. Right, and for my negative as well. Actually, before I do that, sorry to make you guys wait so much for me to explain this goddamn thing. I'm gonna flip it so it's easier to see, and also the symbol looks something like this. We'll go over what the symbol actually is for a capacitor. And so it will get plugged in just like that, and this side will also get plugged in. And you see what happens is when it gets plugged in, obviously before I plug them in, this was empty. This was just two insulating plates that are neutral. And there is no electric field or anything. That's how it basically looked like until I plug them in, where my positives over time, this doesn't happen instantly, depending on how big the capacitor is. If the capacitor is really small, it'll fill up quickly. If the capacitor is really big, then, well, it'll fill up slower. And so what happens is these positives will start walking across. And why do they walk across? Well, this right here is a conductor, this wire is a conductor, and this capacitor plate is also a conductor. Remember up here we said, well, the electrical potential inside a conductor is the same everywhere. So since this is all connected, then the electrical potential has to be the same everywhere. And so that means these will keep moving until my V becomes the same everywhere, because this is all conductors, right? And so V equals constant. So when V equals constant, it stops flowing. And the same thing will happen on the negative side. They'll flow until they accumulate here. And remember, the accumulation here, the number of Q's inside here is the same number of charges, Q's, inside here. Now you might think, why? Why aren't they just different? What if I do make them different? And the thing is, well, maybe you can force them to be different, and then your whole electric field is going to be all messed up. But when you plug them in a battery, what's going to happen is all these are going to accumulate here, and all these are going to accumulate here. And if there is more, so there's obviously going to be more, are going to try to come through here to go to the negative. But what the capacitor is going to say, well, hey, we don't have space. We have too many positives here. So now there's more repelling force repelling the positives back as there are repelling the positives towards the negative. And so what happens is this will fill out a certain amount of Q that will match this amount of Q, and then it will stop filling up. And so after it stops filling up, what determines how many Q's go in there? And so this is where I'm going to introduce my first equation. So before I tell you how many Q's, let's talk about a little bit more about capacitance. And well, remember how we said however many charges here is the same amount of charges here, so they match. The reason they match is, well, when these come here, there's going to be some negative 100 volts. And on that side, that has to match. And so that will go here 100, and so they match. Same thing as if I had 1 Q here, a positive, then I'll have to have a negative here, right? And so here, I should explain this in a little bit smaller terms. I take a box and I put 2 positives in here, right? And this in total is 2 coulombs. And I take another box here and I put another 2 coulombs, but negative. And I connect the wire here and I connect the wire here, but they don't touch. You see, the distance here is much bigger than the distance here. And so what happens is these electrons want to be as close as they can. These protons want to be as close as they can to the electrons. So one will leave and will come here. And the second one will leave and come here. Now, if this plate was small enough so that can only hold 1 charge, then there will only be 1 charge, right? And that you won't see 2 of them because there's only 1 coulomb on this side, so there has to be 1 coulomb on that side. And well, if I make this size bigger, then I'll get 2 here and 2 there, and they match. And so that's practically the same thing when it comes to here. And the equation says is that my Q on a capacitor equals the capacitance of the capacitor times the voltage, or the potential difference. And so what this is trying to say is that my capacitance, how much this plate handles, is directly proportional to how many charges and potential difference there are. Well, sorry, it's the other way. The amount of capacitance it handles is Q over the potential difference equals my C. But the C actually relies on something, well, a bigger issue is, like we said earlier, if mine can only hold, if the size is only available for 1 electron, then it'll only hold 1 electron. And so the C depends on something else. And I'm going to introduce now my second equation. And so my second equation here is C equals epsilon naught times the area over D. Now the area, I'm talking specifically about the area of this plate. And so that is my area, is whatever this times how wide it is, right? X times Y. And so my area equals x times y. Now, it also depends on the distance apart they are. And that would be d. And now, why does capacitance depend on the way it's built? Well, one, if I have a bigger area, I can hold more charge. And if I can hold more charge, then, well, I'll have a bigger Q. And it's also about the distance. But why is that? Well, think about it this way. Let's delete all this nonsense stuff since I've already explained it. And actually, no, that's a beautiful diagram. I'm not going to mess it up. I'll draw another one. And so if I have a plate here, and this has some positives, right? And I have another plate here, which is negative. Right? And there's some wire to some battery that it's going to. Now, the thing is, if I take the distance here and I take it further, then the electric field is obviously weaker because the distance is bigger. And if that's the case, then there's a problem, is that this doesn't attract as many positives as you can because there isn't as much force. Remember, my electric field, the further we get away from it, the weaker it gets. It's stronger here and it's weakest there, and vice versa. The electric field that this is causing is stronger here and the weakest here. But if I increase the distance between them, then that weakens the whole attraction force. Remember, if I have a plus here and I have a negative here, they have a very strong attraction force, just like if you have a magnet close to another one. As I take it away, you can, even when you hold a magnet, as you take the magnet like further apart, now it's easier to pull apart. But when they're very close, it's so hard to pull them apart. And so as I take this further and I increase the distance, my capacitance lowers because the amount of attraction is not as strong anymore. And so while here I attracted some amount of Q, if I, double the distance, let's say, I probably will half the Q. I'm not even sure if this is true, but, well, we can test it here. So look, if I take my distance and I divide it by 2, then by flip and multiply, what I'll get is, well, 2 epsilon naught A over D. Now, if I divide by 2, right, this equals C. If I divide by 2 on both sides, then this will cancel out, and I'll get C divided by 2. Now, taking my capacitance and putting it on this side, what I'll get is C over 2 equals Q over the potential difference. Well, in this case, can I take 2 to the other side? And so I see my C now becomes 2 Q over V. And that actually completely contradicts, because I actually have to, well, actually it doesn't contradict what I said, but I half the distance. So if I was trying to make a point, I made it the complete opposite. So if I have a distance here and I halved the distance, so I didn't actually multiply the distance, I halved the distance. So now I brought it close by half. And so now the force got so much stronger because it's so much closer. And so it doubled the amount of Q I can attract. And so if I actually do the other way, which I was talking about, instead of dividing it by 2, I'll multiply by 2. And you'll find out that this will actually divide Q by half. So if I double my distance, the attraction becomes, well, weaker. And therefore, I can't attract as many charges as I could before. And so the charges also will be cut in half. And so I hope that explains capacitors pretty well. These are the 2 important equations. And so one of them is C equals, well, I believe they go like Q equals C, potential difference V. And the potential difference is obviously the potential difference between this point and this point. The other one is also, where is it? That's C equals epsilon naught A over D. All right. And so also you can think about it that if I make my area bigger, so like I said, if I make the plate bigger, well, more electrons fit inside, and if more electrons fit inside, the capacitance increases, and if the capacitance increases, so on. All right, so you see here, if I double my area, then I will divide my capacitance by 2. And if I take capacitance and I put it this side by 2, and I take 2 to the other side, then I double my Q if I double my area. And now there's a couple more things I want to mention about capacitance. So now the other thing I wanted to mention about capacitance is, well, how do you calculate the charge? or well, not the charge, the electric potential. And so if I go down here and I draw another diagram, so let's make a battery that has some bottom this and some top that, right? And this part is negative, this part is positive, this battery has, let's say, 9 volts, right? That's the potential difference. And so if I connect this, a capacitor, and the capacitor logo looks exactly like a capacitor, which is I have a plate and I have a second plate. But obviously it's like something closer like this. All right. Now, what is the voltage at this capacitor? And well, since this is a conductor, this is a conductor, and this is a conductor, then this is the same thing as if I had basically a little tiny battery in here. Oops. The positive side and negative side. That's basically what it looks like, doesn't it? What's the difference between this battery and this? There's not much besides the chemical reaction. And so the electrons will flow up, the protons, and they'll flow up this side. And now I have a bunch of negatives here, and I have a bunch of positives here. And the potential difference is the same as the battery. It's 9. Why is that? Is because, well, the potential difference between this point and this point is 9, right? And so all I did here was take these 2 points and just bring them closer together. That's all I did. That's what a capacitor does. And so there's still 9 here. So that's one thing. This is in series. And now let's do it in parallel. What does parallel mean? Is what if I add one more capacitor? So let's get rid of these. You know what? I might as well just delete the whole fucking logo. Hello? Alright. So parallel is basically I'll add one more capacitor. And I'll have one here, and I'll still have, let's put that. All right, now, what is the potential difference here? Well, like I said, the electrons will move, and all I did here was split my positive into 2 positives, but the potential difference is still the same. There's still 9 volts across each capacitor. It doesn't really make a difference because remember, my voltage is, well, let me pop up the equation. It's E divided by S, and S being the distance here. Well, assuming the distance is the same, and this is the same capacitor, so both capacitors take some type of capacitance, let's say. My volts, as you see, it depends on the electric field, and the electric field will stay the same. I mean, I haven't changed anything here, so the voltage will stay the same across as well. And the second thing is, actually, even if I were to change the electric field, and if that confuses you, there's a simpler way to imagine it besides this weird looking equation, is that, well, the electrons, well, you know how in a conductor, we said earlier, if I have a conductor, conductor, is it ER or OR? I don't even know. In a conductor, the potential difference between one point and another is the same. I mean, my E is 0 in a conductor, but my potential difference or electrical potential is, well, sorry, my difference is 0 because the electrical potential between 2 points is the exact same. So when I do, let's say this is 100, that means this is also 100. And so 100 minus 100 is 0. That's why you get a 0 here. So that's a trait of conductors. And so, well, this is a conductor. This is also a conductor. And this is also a conductor. So that means if it's 9 volts here, then it's 9 volts here. And it's 9 volts on this plate. And so that means this is also a conductor. And this is also a conductor. So, and there also has to be 9 volts there, because the electrical potential in a conductor is the same everywhere. And so that's the same thing for the bottom part. It's just this will be negative 9 volts. This will be negative 9 volts and negative 9 volts, right? Now, obviously, we don't think about a negative because we like to use it it goes from 0 to 9 volts as the potential difference. So it would be like 0 volts on this side, you could say, and 9 there. All right. And so now after this, we are going to learn how to add these up, how to add these capacitances up. But what differentiates, there's one more thing. So let me clean these drawings up. I just fucked it up trying to clean it. All right. So the other thing that's different about capacitors is that, you know how we said, well, in capacitors, so here, capacitors have same potential, electrical potential. All right, so that's point number one, potential. And this is in parallel. All right, and so in parallel, capacitors have the same electrical potential, but what about their Q? Well, the charge here is a finite amount of positives. It's not unlimited, there's only a certain amount. So when I connect it, then all these will start flowing, and I'll get a certain amount here, and I'll get a certain amount here. Right? And so they don't both have the same Q. Q differentiates on each plate, and that has to do with capacitance. Now let's say this has a capacitance of only 10 coulombs, right? Like, well, capacitance is measured in farads. What I'm trying to have you imagine is that this can only hold 10 charges, okay? And this can hold 20 charges. And obviously, let's say I have 30 charges in here. Then I won't get 10 charges here and 10 charges here. I'll get 10 charges here and 20 charges here. And so you see the Q is not the same across in parallel. So Q not same in parallel. And well, my other question is, well then, is the capacitance the same in parallel? Well, that doesn't matter. I could put a 10 farads capacitor here, and I can connect to my circuit a 30 farad capacitor. And these are huge capacitors, by the way. Usually it's in like microfarads. But let's say I do that. So, well, capacitance is not the same nor different. It's up to you. And so capacitance is up to you. Now, if they both have the same charge, if it's in parallel, they both have the same electric potential and they both have the same amount of Qs, then their capacitance is the same. That just doesn't make sense. But if their Q was different, that means the capacitance is the different for each one. And then there's ways to calculate it. And the equation to calculate it, I'm going to pull it up right now. Okay, so if I want to find the capacitance of this whole thing, of the whole series, of the whole parallel circuit, then what I'll do, well, I know the potential difference, like we said, well, it's the same across both of them. So if I name this number 1, name this number 2, then I know, oh my gosh, boom. If I name this 1 and 2, then the potential difference, V1, equals the potential difference, V2. Remember how we said these are all conductors, and on the conductor, the potential difference has to be the exact same, and so that's why they're equal. Now my Q, well, my Q is not necessarily the same. And so what I can say, well, then Q total, the total amount of Q I have is equals to, well, the Q inside here plus the Q inside here. So that would be Q1 plus Q2. And well, my V1 equals my V2, which just equals my V total. They're all the same. And well, what is my C equal? Where like if I were to combine both of these together. Because, right, I want to find the total capacitance in the circuit. And so, well, if that's the case, I know C equals, where is the equation? CV, right? Oh, sorry, C equals Q over V? Yep. Q over the potential difference V. Now, if I have two of them, so if I have C1 and I have C2 like in my case, then, well, this plus C2 is what you do, right? To add them together. The reason this works is because, well, remember, the total is the same. So what I'll have is Q over delta V plus, that's Q1, V1, plus Q2 over V2. Now these two V's are the exact same. And so then I have, well, Q1 plus Q2 all over 1V. And if I combine these two Q's into my Q total, then now I have Q total over the potential difference. And the potential difference is the same, whether it's total, whether it's 2, whether it's 1, it's all equal. And so now I have Q over V, and that equals C. But which C is that? That is the C total, right? That is this, both C's combined in one. And so now if you give me a potential difference 9, right? So if I give you a 9, and I give you how many charges I have inside here, you're able to tell me the total capacitance. And if I give you the capacitance of both of them, you can tell me how much charge there is. Or if I give you both of these, then you can give me the voltage, right? And so if I have the equal and I have the potential difference, then, well, I can separate this and I say, well, then my C equals my C1 plus my C2 plus my C3 plus my C4 and so on. Okay, you can just add them, and that's in parallel. All right, so keep that in mind, it's in parallel. All right, now we are going to be going into the final part of capacitors, and that is series. Series are a little bit less fun than capacitors. There's less things going on, really. And so here, like we always do, first we start with our little battery, and I wrote it the other way, lol. Oops. And so my battery right here. All right, and I also have my negative side. All right. Dude, sometimes I be having some crazy intrusive thoughts. Anyways, so this capacitor here, if I put one capacitor, right, and I get a little negative and another capacitor, right, and that goes about all the way. Now, when I connect these two, I don't know why I made them so squished together like this, so I'm gonna give them a little distance. Give them a little distance here. Boom. I think that distance just became the same. Lol. Okay, and I'll just keep one here, and I'll put one here, and there you go. Now, when I turn this on, when I turn this whole circuit on, what happens is I'll get some little protons, and they'll come like right here. Actually, I'll put them in red and I'll zoom in. So what happens is I will get little guys right here, right? And I'll also get little guys at the bottom. Right, now when this happens, you can see that obviously the space is no joke. The space that I have here is not a joke. Remember how I told you there's an insulator here that keeps charge from crossing over? So charge doesn't actually cross over. So this middle part, this is just conductor, conductor, conductor. This is just literally a wire that looks like an eye, right? And so when this happens, what happens is, well, this conductor has electrons and protons inside. This is a neutral conductor. Every conductor has some type of protons and electrons inside. It's just they're even. There's the same amount of electrons as there are protons, and they get married and they're equal to each other, and there's no forced neutral, right? There's no odd singles. And so when it comes to this, and I have an excess positive charge here, and I have an excess negative charge here, what happens is the charges inside this conductor will split apart. Remember, when we had a ball, and this was a conductor, and it has plus negative all the side, and I bring a little inductor, or even inductor or a conductor, if I bring it that has a lot of positives, what will happen is the electrons will leave these two positives, and obviously there's more positives here, negative, positive, negative, positive, negative, positive, negative, and what happens is all these little negatives will move, right? These positives will stay where they're at, but all these negatives will move and they'll go right on the side here. And that will create charge separation, where you have a lot of, remember, negatives are free to move inside conductors. Electrons are free to move inside conductors. And so they'll move on the left, leaving a lot of positive on the right, on the left, empty. And all the electrons will move to the right. And so it will turn in half, and this is charge separation. All right? And so now this thing happens exactly the same with this, our little wire conductor right here, is that these charges, well, I still have positives and negatives on this side, right? And I used to, this was neutral. Remember, when this was neutral, there were these negatives here. But when I turned it on, because I got this excess here, all these negatives left these positives and they went here. And so what I get is negatives on this side, right on this side. Now this whole thing, the charge on this little conductor, I'm trying to make it pretty, man. All right, the charge inside here is still Q. Well, actually, it's neutral, so it's not even Q. This side is like, let me get this skinny. This side is Q negative. This side is Q positive, but they're the same amount of Q. So when you add them together, this whole metal piece is still neutral. It's just now we have charge separation. And so, okay, well, in this case, if this attracts, let's say, a Q positive, then the Q positive on this side is the same Q positive on that side. Following so far? That's true. Because it's not going to attract more than, so if I have like 2Q here, it's not going to attract a Q, it's going to attract 2Q. And so it'll only attract what it has. And so that will separate and it will go there. Then this part will be positive and that will also attract the same amount of, well, if this was 1Q plus, then I'll have 1Q minus here. And you notice this is the same thing. Then I have the same amount of charges here as I do here. While I still have two capacitors. These are still two separate capacitors. But since they're in series, their Qs are the same. And that's one thing earlier that was not true. You see, when I go up here, my equation, Q is not the same in parallel because it just divides. However, here, it can't really divide. And so the Q that accumulates here is the same Q that will accumulate here. And so Q in series, so this is series. I believe, how's series spelled? Series capacitor. All right. Q is the same across both capacitors. Now, okay, let's think about then the potential difference. Is the potential difference the same across? And now when it comes to potential difference, what is the potential difference in a series? Well, we know that, where's my mouse? My mouse, oh, there it is. Okay, so I know that obviously here there is, well, we said, remember, at the negative side of it, we have a potential difference of 0. And so at the positive side, we have some potential difference V1. And well, here there's also a potential difference between these two. And so here we have some potential difference V1. And at this end, we have, well, a potential difference of 0. Well, here we'll name this V2. And here we have a potential difference of 0. And so as you can see here, then the total potential difference, well, here we have right 9 volts. Then this gets separated on 2 sections. And therefore, the total potential difference here, the total electric potential is the addition of both electric potentials. Addition of V1 plus V2 equals my 9 volts, right? And so it separates on 2 sections, but my Q, remember, my Q stays on only 1 section. And that's really it. So if I go to my parallel, just to make sure I'm consistent with the points, C, it's up to you. Oh, lol, C is up to you. But here, remember before how we added it? In parallel, we said, well, C equals Q over V. And then if we have 2 C's, then the C, both of them combined. If I want to combine both these, let's say C1, C2, equals Q2 over V2. And I said, if I want to combine these into one, then I can just say, well, these V's, since they're the same in parallel, I'm talking about parallel here. Since they're the same in parallel, then that's just Q1 plus Q2 over V, because the V is the same. And so this is the same thing as saying C1 plus C2 plus C3, and so on. But for this case, now what I have is, well, CEQ equals Q1 plus Q2 all over V1 over V2. Now, I can't add these together because the denominator is not the same anymore. But I can add their inverse. And so if I inverse this, what I'll get is CEQ. Well, I'll get 1 over. I got to inverse both sides. Right? Equals V1 plus V2 all over Q1, Q2. Now, these two are the same. Remember, in series, the charge is the same. Q is the same. And so 1 over CEQ equals V1 plus V2 all over the same Q, because Q is the same. And so writing this out, well, I know C equals Q over V. That means 1 over C equals V over Q. And so I could say then, yeah, this CEQ, which is the total, equals my 1 over C plus 1 over C1 plus 1 over C2 plus 1 over C3, so on. But obviously, that looks ugly as shit. So what we'll say is, you know what? CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3 dot 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 all to the negative 1. And that is your total C. All right. That's series and parallel covered for capacitors. And we have a little bit more for this unit before we wrap up. All right, so I was gonna cover the last dielectrics and electric field, or I believe he did dielectric and insulators. I can't believe, but this last video he posted is like 18 minutes long. I'm not gonna go through it because all the equations he showed in there were not on the formula sheet, so I don't think they're coming on the exam. I've already spoke to the prof and he confirmed. He said, I'm not gonna have you memorize anything. We're only gonna be using what's on the formula sheet. So, but I would say definitely go watch it in case you do run into it, so you know what to do. All right, so now to practice problems. How much work does the charge escalator, the charge escalator do to move 1 microcoulomb of charge from a negative terminal to the positive terminal of a 1.5 volt battery? And so if I have a battery right here, that's my little battery, and I have a negative terminal and I have a positive terminal. This is how it usually looks like. And it's saying how much work does the escalator do to move 1 microcoulomb of charge. So if I have one microcoulomb, which is times 10 to the negative 6, I believe. So which equation am I going to use for this? Now, well, I know my electric potential equation, U gives me my work, which equals the Q, V. So if I have a 1.5 volt terminal and I have a Q, how much work does it do? Well, 1 times 10 to the negative 6. Remember, this is coulombs, right? And my volts is 1.5, and this is joules per coulomb. And so these two will cancel out, and what I'll get is 1 times 10 to the negative 6 times 1.5. And that gave me 1.5 times 10, 1, 2, 3, 4, 5, 6, times 10 to the negative 6 joules, right? And that is question number 1. Sweet. Now, question number 2 says, 2 3-centimeter diameter aluminum electrodes are spaced. Okay, so first let's make these electrodes. So I have my part 1, and I have my part, there you go. And so these electrodes look something like this, right? and they're spaced some distance apart. And the distance they're talking about is 0.0, well, that's very small actually. I'll just write it in millimeters then, I'll convert it later. 0.05 millimeters. And these two, they have a diameter, so they're obviously circle shaped if they have a diameter. And this is each electrode, and each electrode has a distance d across. This distance is equals to 3 centimeters. All right. Now saying the electrodes are connected to a 100-volt battery. So these are connected to a 100. This is a battery symbol. Oops. They're connected something like this. All right. Where you have a positive, well, this would be a negative according to my thing. And so this will be negative. This will be positively charged. And what is it asking? What is the capacitance? So if I write this in a simpler circuit, you would just get, that's what it would really look like. And so the capacitance in my circuit, well, I have a couple equations to choose from. Do I have voltage? Yes. So the voltage that I have here, which is stated to be 100 volts, well, that's the same voltage here. Right, so the potential difference between here is 100 volts. It's the same across the capacitor, because this is all a conductor. So if the voltage here is 100, then this has to be 100. Remember, electric potential inside a conductor is the same everywhere. And this is all conductors except this space here is an insulator. Or an electrolyte, whatever they call them. Dielectrics, they're called, whatever they put between this. Dielectrics. And anyways, so the equation I have is, well, the change in VC equals the charge over my C. And so, well, what do I have and what do I not have? Now, it says two of them, 0.5 part. The electrodes are 100, so this I have. Oops. This I have. Do I have my Q? No. So I don't have my Q. And I'm looking for my capacitance. Well, I know the capacitance equation equals C epsilon naught A over D. And D is this distance, not the diameter. And the area, well, the area of a circle, so epsilon naught, the area of a circle is 2 pi r, I believe. Is it r squared or 2 pi r? Let me check. It's actually pi r squared. So pi r squared over d. D is the distance between them. So what I have is epsilon naught times pi times r squared, which is, well, this is this is 3 centimeters. Half of 3 centimeters is 1.5 centimeters. So this is 0.015 meters squared all over the distance. And the distance I have here, which is well, that's millimeter. Let's convert that to meters. Millimeters to meters. I don't even know, 0.05. That is 3 zeros and then a 5. 1, 2, 3, and a 5. So plugging these things in, what do I get? So what I got here is 1.25 times 10 to the negative 11 farads. Now my answer isn't picos, so rounding this up, this will be 13 picofarads. All right. Now moving on to the next question, or part B. What is the magnitude of the charge on each electrode? What is the magnitude of the charge? So how many charges? So what's Q on each electrode? And now, obviously, since I know my capacitance here is to be 13, I'll keep them in farads actually, so I'll remove the 13. I'll use the farads. Now, obviously, I'll use this equation. And so what I got is the change in VC equals the Q over my C. Now, I got my C right here, and I got this VC, which is 100. So I got 100 times 1.25 times 10 to the negative 11 equals my Q. And so doing that, timesing this by 100, what I'll get is, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9. And so what I got is 1 times 10 to the negative 9 equals Q, which is the same thing as 1 nanocoulomb equals Q. Now they did get 1.3, which I think that is like rounding. I'd assume because they probably use 13 for this. I could try to use 13 instead. I could cancel this and use 13 or 1.3. So let's see, 1.3 times 10 to the negative 11 times 100. Oh, times 100. I still got 0.1, so I'm not sure how they got 1.3. I'm just assuming it's like they have a extra decimal. All right, so I just confirmed this for you guys, and it is a rounding issue, so this would technically be right. Question number 3, it says you need to construct, so I need to construct a 100 picofarads capacitor. So let's create this 100 picofarads capacitor. I got my this side. Actually, before I do this, I'll just keep this instead. Delete all my equations here. Remove all this stuff. I feel like this is faster to accomplish. I lied. I think that actually took longer. Well, now this is my 2 electrodes for my capacitor they want us, and we're here if you're wondering. All right, so this has to be 100. So my capacity equals 100 picofarads. All right. My capacitor is 100 picofarads, and you plan to cut 2 L times L metal squares and insert a small spacer between them, between their corners. Huh? Okay, so there's some insulator here. Where's my square? I guess there's no square. Anyways, this is my dielectric. And this, the area of electrode is L squared, because L times L is just L squared. The thinnest spacer you have is 0.20 millimeters. So they're saying basically the space between this is 0.20 millimeters. So 0.2 millimeters thick. What is the proper value of L? Well, we know my capacitance equals my lambda over A divided by my D. And so my D is 0.2. So converting everything in the same, so millimeters, well, actually I remember it from last question. The conversion, well, here I still have my 100 and picofarads. I don't know what picofarads are, so let's search up what is 100 picofarads to farads, and what I'll get is times 10 to the 12 times 10 to the negative times 1. Oh, can't even speak. And what I'll get is 1 times 10 to the negative 10. That's my that's in farads. Equals my E, and my epsilon is a constant. My A is what I'm looking for, and my D is the conversion of 0.2 to meters, which is 0.0002. Now the reason I need this in meters is because your epsilon is measured in meters squared per coulombs or something like that, so that's why you got to convert it. Now after this is done, take this to the other side, take epsilon to the bottom. I'll get 1 times 10 to the negative 10 times 0.0002 all over my epsilon naught, which is 8.85 times 10 to the negative 12. This will equal my A. And we're not done yet, by the way, because we're looking for L. So I got to take whatever this is, because remember, A equals L squared. So in order for me to get L, I have to square root A. And if I have to square root A, that means I have to square root this whole thing. And so the square root division, 1 times 10 to the negative 10. And by the way, I hope you guys don't leave when I'm doing the calculations, because sometimes I do make mistakes. So when I get my answer, I find out that there is a mistake. And so just so you guys don't learn the wrong solution. Like, don't see this like, oh, I'm done, because I might be wrong. Okay, but anyways, what I got is 0.047 meters, and that's 4.8 centimeters, which makes sense because this is in meters. So yeah. Okay, moving on. Next question. Right, now we have a series capacitor for this question. And this question has, well, a battery, right? And this battery will go up top. Nice. And across. And since it's series, I know the capacitor somewhere is going to be on this side. My line doesn't want to straighten. Nice. All right. So before I read, I just saw capacitor, so I just decided to draw it. Now it's a 6 microfarads capacitor. So let me put that capacitor in. This is the capacitor, right? And this is, I'll name it my C1, right? And now going down, do I have another capacitor? A 10, oh wait, what? What is the question? A 6 microfarads capacitor, a 10 microfarads capacitor, and a 16 microfarads capacitor are connected in series. So I have this one, I have this one, and I have this one. And I assume that's where it ends. Alright, so I just gotta draw my diagram. This is C1, that is C2, and that is C3. Now, if you remember, series capacitor Q is same. Potential difference is different. Also, the equation is given. Your C equals 1 over C1 plus 1 over C2 plus 1 over C3 dot 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 to the negative 1. And now what are we looking for? Saying what is their equivalent capacitance? This is the equivalent capacitance. So equivalent capacitance means basically if you combine all these into one capacitor, what would that one capacitor be? Or what are the characteristics of that one capacitor? And so, well, let me get my C1. And obviously my C1 equals to, they gave it to me. I have it right here, 6, 10, and 16. So 6, 10, 16, and all of these are in picofarads. Or is it micro? Yeah, it's micro, my bad. 16 microfarads. Alright, and so all I gotta do is put the 6 here, plus 1 over 10, plus 1 over 16, all to the negative 1. And see now, I mean, this is pretty simple, assuming I did it right. 1 over 6 plus, oops, plus 1 over 10 plus 1 over 16 all to the negative 1. And I got a total of 3.037. Since I kept it in pico, then my answer is also in pico. And is that the same answer? That is. Okay, so next question. All right, this question finally gives us an actual diagram. So let's steal that bish like we always do. Nice. And there you go. Now the question says, what is the equivalent capacitance of the three capacitors? So we're going to take this, this, and this, and get a total or equivalent capacitance, put them all in one capacitor. What would that look like? Well, first, let's take this section. You want to always split your problem in two in physics. And now this section actually looks like a parallel. And so, well, if I convert this into one circuit, that would look like a battery connected to these two. Oh. Oops, I actually did that wrong. Well, actually, that would be the same. So if I put, yeah, so it's like this, and it splits off like that. That's basically what this looks like. Now, if I draw it exactly the same, I could put my battery up top here, and this will still, you see, split off into two different roads. I have one junction point here, and then they go separately, and they come back together. And usually this obviously has to go to the back of the thing, but that's how it looked like. I just put a battery in here, and obviously this end will connect to the back of the battery, or you get the point. And so now using this, since this is a parallel, what I can say is, let me get rid of all this gibberish. Parallel circuits, my Q is different. But my V is same. And if we remember using this property, the C equivalent in a parallel, remember, I'm only doing this right now, equivalent of C1 plus C2. So let's do that. So now I have C equivalent, which is, let's say I'm combining this into one, is just 10 plus 20, which equals 30 microfarads, and that's my C equal, and I'm going to name this number 1. Now, if I take this and redraw it, but since I got this in terms of only one capacitor, I'm going to place that whole section with just one capacitor. And so let's do that. And so I have my battery. Right, now this is the capacitor that I just combined. This was two capacitors in parallel, but I just combined it. And so this is now my CEQ1. Right, and it looks something like this. And this is, I can name this my, let's name these actually, C1, C2, C3. I don't know why I named that in reverse, but C3. So now this now is series. And so, okay, well, how can I add the capacitance in series? And we just did this last question. That's 1 over C equal, but remember we're going to raise it. So it's going to be C equals 1 over C1 plus 1 over the next one, which in this case is CEQ1, all to the negative 1. And what that will be is 1 over, what's this capacitor C3? It's 10 plus 1 over 3, all to the negative 1. And this is, sorry, this is not 3, this is 30. I don't know why I have it as 3. Right? I have 20 and 10. Yeah, this is 30 micro. And so, oops, sorry about that. And now equals, what I have is 1 divided by 10 plus 1 divided by 30, all to the negative 1. And what I get is a nice number of 7.5 microfarads. And what I did here, basically, this new C equal 2 is basically I'm having my battery, a good looking battery, and I just replaced all these 3 capacitors with just one capacitor of 7.5. And this basically does the same thing. All right, now next question. All right, so for this question, it's saying a 2.0 centimeter diameter parallel plate. And so first the diameter, so that is a circular plate, all right, which has a diameter D. And this D equals 2 centimeters. All right, now these face each other. So I have one, and this is looking at the circle that I just drew from the side. All right. And now what it says is they're parallel plate capacitors with a spacing of 0.5 millimeter. So now the spacing between them, 0.5 millimeters. Is charged to 200 volts. So this is connected to something. And obviously this something is a battery. All right. And so this is charged to 200 volts. What are the total, well, A, the total energy stored in the electric field, and B, the energy density. And so the electric field inside this is an equation given. So let me pop it up. Okay, so actually, I just remember this is not an equation given in the sheet, and this is the last video that I told you to watch. The equation, and thank God I remember it. I don't want to run through the videos right now. 1 over 2 C VC squared. This gives you the work done, or in other words, the total energy stored, right? Energy is joules, and this is joules, right? And so what I need in order to calculate this, well, I need, well, 1 over 2 is a constant. I need capacitance. Does this give me capacitance? Let me see. So equivalent capacitance of 3 capacitors. If I have the separation and I have the area, I can calculate the capacitance of this capacitor, because capacitance equals E naught A over D. Right? So I have A, which is, well, that's pi r squared, and I have diameter, so I can get the area. D is the separation, which is 0.5 millimeters. So now C is given, and I know I can find it. Moving on to my next variable, and this is, by the way, how I solve my stuff in exams and tests, is that I don't really go through numbers and try to figure out. First, I work at it backwards. Dude, what do you... I got dang interrupted in the middle of my question or my thought. Back to my question. Anyways, so we do have 200 volts here, which is, that's good. Now I can just sub that in. So that's 200 here. 2. Now my C, let me grab that from up here. Well, obviously, I know my C equals my epsilon naught. My area, well, that's pi. Well, my R is 0.02 would be my diameter, and 0.1 divided by 2 will be my radius. And so we're going to take that whole thing, we're going to square it, and then we're going to divide it by the distance, which is 0.5 millimeters, but in meters, that's 0.05. All right, now calculating this whole thing, I'm plugging into my calculator right here. I got 8.85 times 10 to the negative 12. Whoops. All times pi, and then that is all times 0.01 squared and 0.0005. That gave me a nice capacitance of 5.56 times 10 to the negative 12, and that's in farads. So in pico, I believe this would be 5.56 picofarads. And so plugging that in here, well, I get is 1 over 2. And this will be 5.56 times 10 to the negative 12. This will be 200 squared. And so timesing this by 0.5 for the half, and then timesing it by 200 squared. What I got is 0. What is this? 1, 2, 3, 4, 5, 6, 7. That's 1.11 times 10 to the negative 7 joules. Now, did I get that right? 1.1. Oh, dude, too good. Too good at what I do. What can I say? Wait. I was not done yet. There's a part B. Lol. Part P is the energy density. Well, now, since I have my joules and I have my capacitance, well, to be honest, I was thinking for an equation, and then, well, I know I have my capacitance, but, well, what is density? Density is some joules per something, and they're looking for the energy density inside this area, right? Because that's where the energy gets stored. If you watch the last lecture for Joseph's, the energy gets stored inside here somewhere in the electric field. And so, well, my energy density will be whatever joules I have, which is this amount, right? That's what gets stored inside this capacitor. And, well, how much gets stored inside this density? And so this is, well, I gotta get the area, well, the volume of this area. All right, and so that would be, how do you get the volume of a cube? It's length times width times height, and so we know the length is 2 times width, which is also 2 centimeters. So this is, right, this is 2 centimeters, and the width, so this is what it looks like, connected like this, right? We know this is 2, and we know this is 2. This is the plate. You can think about it. These are the 2 plates. And this area in between, this D, is the 0.5 millimeters, right? And so if you times all these 3 together, you'll get your volume. And so turning that to meters, 0.02, yeah, that's in the centimeters to meters, times, well, these are actually a circle. So actually I need a volume of a sphere. So it's not a square. It's actually a circle. So volume of a sphere, let's see what that is. Volume of sphere. Volume of sphere is 4 over 3 pi r cubed. Now this area in the middle here, this little sphere, well, this is a circle, would be a circle. So actually it's not, I made a mistake, it's not even a sphere, it's a cylinder, because I have one plate like this. So looking at it from the side, I have, this is a circle, and then I have a straight line, and I have another circle. So looking at it from the top, I'll have a circle like this, and it goes down, and then I have another circle down here. These are the 2 plates, and that is the space in between. So it's a cylinder. So I need volume of a cylinder. Volume of cylinder. And that is pi r times height. And so that would be pi r squared, which is the area. Pi r squared, which is the area of this circle. and then times the height, which is my distance d, which is 0.5 millimeters, right? Times my height. And so if I take this, do the arithmetic here, which is pi, times my r, which is 0.01 all in meters squared, times my height, which is 0.0005, right? Millimeters to meters, just to confirm one more time. If I have 0.5, yep, we got that right. And so doing this here, what I'll get is pi 0.01 squared times 0.0005. What this would give me is 1, 2, 3, 4, 5, 6, 7. 1.57 times 10 to the negative 7, right? 1, 2, 3, 4, 5, 6, 7. Yep, this is meters cubed because it's a volume. And now we have this many joules for this much. So what's the density? Divide one by the other. And so if I take the division of 1.11 times 10 to the negative 7 divided by my area, what I'll get, my volume. So what I did here is 1.11. I have this many joules, right, per this much space. What's my density? How many joules do I have per meter cubed? And so what I got is 0.71, and this is joules per meter cubed, right? At the bottom is meter cubed, at the top is joules. And if I look at my answer, 0.71 joules per meter cubed. Now, next question, question 7. We have two 4 centimeter by 4 centimeter metal plates. So this is a square this time. So unlike all the other times, this is a square. Let's get my first plate, get my second plate. Nice. Right? And so here I have a negative, and here I have a positive. That's usually what a capacitor is. Now it doesn't say, it says electrode, so it's a capacitor. And it's spaced this time, and I'm going to convert this right away this time. We have 1 millimeter, so before it was 0.0005, but since this is 1, it would be 1. But that one was 0.1, this is 1, so that's what it looks like. That's how I usually convert my stuff in my head. Obviously on faster rate. But anyways, and I got it wrong. Wrong question. It's separated by 20. All right. Okay, so we got that right. And this is 4 by 4 metal plates. So these plates, if I write them on the side from the front view, they look something like this, and it's 4 by 4. These are centimeters, so let me convert them to meters. 0.0. And I think this deletes it, no? Aha, let's go. There you go. All right. And so piece of Teflon. So whatever Teflon is. So the dielectric Teflon. All right. And so since we have that, what is the capacitance? Now, because of our dielectric, if you watched the last lecture that he did, that I told you to watch, that I didn't cover, dielectrics do cover the capacitance of your capacitor. So when you put just air, and when you put water will cause you to have a greater capacitance than if you were just to have air. And so we're going to have to find the capacitance of the Teflon. So I've got to search that up. It's a constant. Actually, I just thought about it. I'll cover the unit right now real quick within this question. And so each material that goes in between has some value, fancy looking K. I don't even know what this K equal means, but it's like, you know, a Greek letter, just like micro or what else do we use? You know, alpha, beta. Anyways, so we have this letter K. This K represents the inductance level, you could say, of this material, and it's just a constant letter, a constant value per material. So for example, the examples he used was water has a K value, however this fancy K looks like, a K value of approximately 80. Air is just 1. Right? Paper he also used. I believe it was 7.4 or some shit like that. I'll just say 7.4. This is don't take these values for real. I'm just estimating. But it's something like this. And each paper has its own, each element or material has its own value. And so here we have Teflon. Now, what's the value of Teflon? I haven't grabbed it yet, so I'll have to go grab it. But one thing I do know, my monitor almost fell. I had to fix it. Jeez. This equation is your E, permittivity of free space, divided by this E that this material would create inside, the electric field inside of it. And so you know how if I have Teflon here, if I put Teflon right in the middle, this is a inductor. And in an inductor, obviously the electrons can't move. So if I have a negative side here, if this was a sorry, this is an inductor. If it was a conductor, then all the positives will come on this side, right? Well, they're not gonna come; they're just gonna stay there. But all the negatives would leave to this side. But in an inductor, that's not really possible. They can't move. So what happens is on a molecular level, your atoms will actually, the positive will face the positive and the negative will face. So they'll actually flip like dipoles. And so the plus and the minus. And so this will keep happening all around here. Plus, minus, and one more here. Plus, minus. And you see these two right here would cancel out, and these two would cancel out. But this side doesn't cancel out, and this side doesn't either. And so you find out that right on the edge, you got a bunch of negatives, and right on this side, you got a bunch of positives. And you see inside here, this creates an electric field. And the electric field obviously goes from the positive to the negative, and that's in this direction. But obviously, our regular electric field goes from positive to negative in this direction. And we'll put that as 0. And so this whole phenomena, will make your actual electric field weaker than it seems. By a little bit, by a tiny bit. But when it comes to, obviously, industrial level, these materials, they make them so good that it makes a big difference in capacitance. And so that's why we got to calculate for this little E right here. All right. Now, calculating for it, obviously, we're using this equation. And I believe it goes like something like this. Has to be more than 1. More than or equals to 1. And so my equation is my electric field of C is proportional to the electric field that's created. So E is the total, and E naught, or I believe this one is the E naught. I'm not too sure. Let me confirm that. Yeah, so actually the outside one is your E naught, so it's the other way. Oops, I messed that up. I got my equation wrong. So this is your E naught, and this is your, other way. I messed it up again. Oh wait, so I had it right. Dang! I do be smart sometimes. Alright, never mind. Lol. Okay, so what it's saying now, my V is proportional to the E inside here. Right? And so this does affect it. It does affect it by a big bunch. And so my capacitance will increase as this increases. So if this increases, if the electric field here increases, then my electric potential increases. And if the electric potential increases, so I see this is Q, and this is V, this is the equation. As my electric field increases, then, well, let's say it doubles, then this also doubles, right? And so it's directly proportional to capacitance, and it increases capacitance. Now back to the question at hand, we have Teflon. And so let's, we'll keep all this stuff. Let me go get the constant for Teflon. All right, so my kappa is K for Teflon. So K for Teflon equals 2.1. All right, and so in the equation, what they are asking us for here is what is the capacitance. Now, obviously, I know my capacitance equals C, E naught A over D. My D is given, so let's put everything in here. E naught, my A would be 0.04 times 0.04 all over my D, which is 0.0002. And I'm probably asking, well, okay, we didn't even take into consideration our kappa. And this kappa actually goes right in front. It's just a constant. That's where it goes. Usually we have air, so it's just one we've been doing, so we never wrote it. But there's actually a letter K here, and that's a constant. And so what it would look like is 2.1, and that's for our K kappa. And then we have 8.85 times, that's an ugly looking 8 right there, times negative 12, 0.04 times 0.04 all over 0.002. Oops. So let's see how accurate that is, and let's see if we're right. 2.1, 8.85 times 10 to the negative 12. Yeah, by the way, I don't know if you guys think like I know everything. I don't. I kind of just learn as I'm teaching you guys. Like I figure things out literally when I'm teaching. I'd read the question, I'm like, huh. All right, so yeah, I was just thinking about this. I was like, well, there should be a K there. I think this is right though. 1.4868 times 10 to the negative 10. What did they get? There's a question. They got 0.15 nano. Nano is negative 10. So if I rewrite this and, well, not negative 10, it's negative 12? Sorry, no, negative 9. Yeah, it's negative 9. And so if I take this back once, I will get, well, actually, no, I'll take it forward once. Why am I so confused? Well, let me first do this. 1.5 times 10 to the negative 10. If I take it back once, it will increase by 1. And so it would be 0.15 times 10 to the negative 9. Yeah, see, I'm not really good with basic math, but that is the right answer, so we're happy. What is the maximum potential difference between the plates? So what they're saying is between these two plates, what is my potential difference? V. And now the thing is, obviously, if there's a battery hooked up to this, the battery will be, like, let's say the battery is the battery is marked for 10 volts, then the potential difference there will be 10 volts. But what is the question here? We have the plates, we have capacitor. We're looking for maximum potential difference, and so what we'll do is we'll use a different equation. I'll pull up my formula sheet, and where is my capacitance? Okay, yeah. So the VC equals Q over C. Now capacitance I do have, but Q unfortunately I don't have. So what can I do here? So the thing is we don't have Q, so we're gonna have to use a different equation. But the problem here is the different equation that I want to use is my V equals E times D. And this equation comes from the formula sheet. And if you go up, it's the capacitor, the potential inside a capacitor. All right. So in the formula sheet, it's V equals ES. And S is the separation between the two. And E is the electric field inside, gives you the voltage. Now, what is the maximum? There is something called a breakdown electric field for Teflon, and that is the amount of electric field it can handle before it basically breaks down. And that breakdown electric field, so break down for Teflon is 60 times 10 to the 6 volts per meter. And you see, if I take this and I sub it in here, V equals 60 times 10 to the 6, and I times it by the distance separation, which is 0.0002. Let's do that. 60, oops, I just fucked up my calculator. I gotta restart it. What the hell? Okay, so 60 times 10 to the 6 times 0.1232. I got 12,000. And what's the answer here? 12K. Nice, that's done. Thank you guys for watching. There's 3 more questions. So actually, I was gonna go through these questions, but I'm looking. I read them through, and to be honest, they are regular questions that we've already covered. For example, this one: what are the charges on the potential difference across each capacitor? Well, you turn it all into one capacitor, get the potential difference, split it apart again, get the potential difference, and so on. So I'm gonna leave that for you guys to solve. If you guys need help, comment, and then I'll do them.